Today we're beginning to solve systems, and today we're going to be doing that by graphing. There are two other methods that we'll be using to solve systems of equations, but right now today we're only going to be using graphing. So what is a system of linear equations? Well, a system of linear equations is two or more linear equations. What's a linear equation again? Remember, that's an equation that makes a line. So in this first example, I have two equations that make lines. What we want to know is if 8, negative 1 is a solution, meaning is it on this line and is it on this line? Well, how we're going to be able to tell that is by plugging in our x and our y values and asking ourselves whether or not it's true. So if x is 8 minus if y is negative 1, does that equal 9? And the answer is yes, it does. So yes, it is a solution to the first line. Now the second one, we have to take 2 and we have to plug in the 8 plus 3 times the y, which is negative 1 equals 13. Well, 2 times 8 is 16. 3 times negative 1 is negative 3. Does this equal 13? Yes, it does. Because it works for both equations, it must work for both equations, we can say, yes, it is a solution. This next problem, we're doing the same thing. We're going to check whether or not 2, negative 7 is the solution. So this is my x and this is my y. I'm going to plug in 2 minus my y value is negative 7. Does that equal 9? That's the question we're asking. Yes, it does. So then what I'm going to do is I'm going to plug in my x value and I'm going to plug in my y value and I'm going to ask myself if it equals 13. Well, this gives me 4 plus negative 21. Does that equal 13? No, it does not. Because it does not work for the second equation, this is not a solution to the system. So it can be a solution to one, but not a solution to the other. And if that happens where it's not a solution to the second one or the first one, we know it's not a solution to the system. It has to work for both equations. So there's 3 types of graphs that can occur. So the graphs of linear systems, one of 3 things can happen. You could have intersecting lines. When you get the intersecting lines, this is the solution. So this is the solution. So where they intersect would be the solution, meaning that point is on both of those lines. The second thing that can happen is you could have parallel lines. If you have parallel lines never intersect. So when you have parallel lines, we will say that there is no solution, meaning there is no point of intersection. The third thing that can happen is that you can actually have the graph and you have the same line. You can barely see that. I have a pink line and a green line. They're lying on top of each other, so you have the exact same line. The type of answer we would put here is infinitely many solutions. So on this type of problem, we would have infinitely many solutions, meaning it intersects everywhere, so we don't even know how many solutions there are. There's infinitely many. So if you have intersecting lines, you have one solution. If you have parallel lines, you have no solution. And if you have the same lines, you have infinitely many solutions. Those are very, very, very important. We've got to know those. So when we graph, we're going to graph both the lines on the same coordinate axes. We're going to find their point of intersection. We're going to use the extended slope. So we're going to do rise over run many times so that we can find that point of intersection more easily. And then what we're going to do is we're going to write that intersection point as an XY coordinate. Alright, getting started for this, I said I was going to find their intersection point, and so I will. I am going to use a red pen for this line. What I'm going to do off to the side here is write down what my M and my B is. So I'll be graphing my slope of 2, which I'll make a fraction as 2 over 1, and my B value is 1. So when I graph that, I always graph my B value first, which is my y-intercept. And then from there you go up to, rise to, run 1. Rise to, run 1. Rise to, run 1. Notice how many times I'm doing this. I'm always going to do it many, many times for my first line, and then I probably won't do it as many times for my second line. And also, instead of going up 2 over 1, we've also talked about how we can go negative 2 to the left 1, because that's negative 1. Negative 2 to the left 1. Because what we're really doing is we're doing a negative 2 over a negative 1, which is also a positive 2. So we can continue to do this many times. I'm going to stop for now, and if I need to extend that out further, I will later. So that gives me a nice straight line. Then what I'm going to do is I'm going to change my pen color, and I'm going to make this line blue. And in this problem, I have my m equaling 3. Right there's my slope. And my b value is equal to actually negative 1, because this should be plus the opposite, negative 1. So I'm going to graph negative 1 on my y-axis, and then I'm going to have a slope of 3. Now, 3 would be up 3 over 1. So up 3, 1, 2, 3 over 1. Now, you might think that's where it's intersecting, but it's actually not intersecting there. It's almost intersecting. Then you go up 3, 1, 2, 3 over 1. Right there is where it intersects exactly. Now, how do I know that for sure? Well, I didn't get that line drawn very straight. We'll see if I can draw that a little bit straighter. That's exactly where one of my red dots is. That's how I know it intersects there exactly. The other thing I can do is we're going to have to name this ordered pair because this is the solution to the system. So it's always x comma y, so I'm going out here 2, so that's my x coordinate, and then my y coordinate is 5. Now, to know whether or not this is actually the answer, you can actually check your answer. So we could put 2 in for our x, and we could put 5 in for our y and see if we get a true statement. What's 2 times 2? Well, 2 times 2 is 4, plus 1. Oh yeah, that is 5, so it does work for that equation. The same thing you can do here, you can test it. 3 times 2 is 6. 6 plus negative 1 is, it is 5. So it works for both of the equations, so I definitely know I have the right answer. You can check every single answer every time you do a problem and know whether or not you have it right or wrong before I even check. Let's do another one. So I'll use my red pen for the first line. We've got our slope is negative 2. I'll put that over 1. And my b value is 4. I'm going to graph the y-intercept as 4. I'm going to go down 2 over 1. 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 Many, many times. Or I could have gone up 2 to the left 1. Up 2 to the left 1. And we're just extending that line out as far as we can. That's going to help me be able to find that point of intersection much more quickly. The second line I'll graph in blue. So my slope is being 3, and that would be 3 over 1, and my b is negative 1. So I will plot my negative 1, and then I will go up 3, 1, 2, 3 over 1, boom, I already have my answer. Done. Connect them, find a point of intersection. Point of intersection is right here. That would be the point 1, comma 2, 1, comma 2. You can check your answer by plugging that in. Put 1 in here, put 2 in here. Negative 1 times, or negative 2 times 1 is negative 2. Negative 2 plus 4 is 2. That does work. Plug in 1 here, plug in 2 here. 1 times 3 is 3, plus negative 1 is 2. So they do check out, and it does work. The next one we're going to do is an x equals equation. I haven't done a whole lot of these. When you graph something like this, you can always use t-charts. What this means is that x is always 1. So I can put 1 a ton of times for x. It doesn't matter. It's always 1. And then it doesn't matter what x is 1, y can be whatever I want it to be. So I'll just pick a bunch of different numbers. But x is always 1 because that's exactly what it says. So if I plot 1, 0, I'd be here 1, 1, 1, 2, 1, 3. So what I get is a vertical line, something with undefined slope. The second one I will plot by using my slope of 1/2, and my b value is 4. I should change the color of for each line, but I'm not going to on this problem. So my y-intercept is 4. Plot my 4. And then I'm doing rise 1, run 2. Now on this one, this is one where we don't have the exact intersection. I'm not typically going to give you problems like this for graphing. We'll deal with more of the fraction type answers with the other types of ways we're going to solve. Because graphing, it's hard to see otherwise. I can see that it's basically going between 4 and 5 though, so I'm going to say this intersection is 1, 4.5. Okay. This next one we're going to do, this is the last one in this video and the last one for this section. I first need to solve for y, so I'm going to change this to plus the opposite. I'm going to subtract 3x from both sides. That gives me a negative y equals negative 3x plus 9. Then I can divide by negative 1. Y equals 3x plus negative 9. Plot my negative 9. Rise 3, run 1. Rise 3, run 1. Rise 3, run 1. I can do this many, many times. Rise 3, run 1. Connect my dots together. The next equation, I will have my m is, there's a 1 sitting right here, so m is 1. We can write that as a fraction, 1 over 1. And my b value is actually 0 because there's like a plus 0 here. So my y-intercept 0. I'm going to rise 1, run 1. 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 Again, I've got one of these cases where they don't match up evenly, so I'm going to have to say this is approximately, it's between 4 and 5, so I'll say it's 4.5, comma, here it's between 4 and 5, so I'll say 4.5, comma, 4.5 as my solution.